You and I are living in a very special time, the age of solar system exploration. Our solar system is a complex masterpiece of which we knew so little from our ground-based observations. But within the span of a single lifetime, NASA has sent spacecraft to every planet and several moons, our first eyes to set upon undiscovered lands. Before we endeavored on this journey, everything we knew of Pluto could have fit on a single file card. And now, we downlink new data every day. We first televised pictures of our Earth from space in 1960. Soon after, we were together celebrating our first American orbits, venturing outside to learn to spacewalk, pushing further towards our moon, watching the Earth rise up over the moon's horizon. We learned to coexist peacefully and work together in space, while also taking the time to revel in the simple joy of it all. Look how far we've come, you and I, in our short history of space exploration, all within a single lifetime, all broadcast right to our homes. We've ventured to the very center of our system to observe solar flares peeling off the sun in 3 dimensions. We watch sunsets from the hills of Mars. We monitor storms even larger than the Earth itself on Jupiter. We gaze at the wandering rings of Saturn and ponder the vast unknown as Voyager 1 enters interstellar space after 35 years. By reaching for these new heights, we are looking at data no one has seen before, from regions no one has been before. Space offers the ultimate perspective. It is in our nature to explore, and the reward for this exploration is we learn more about ourselves and our surroundings. Space communications offers us a conduit for bringing this valuable knowledge to the ground. It improves our everyday lives by providing us with information to make better decisions about our planet. What we learn from space tells us more of our own world, and more importantly, what it has in store for us in the future, so we may respond appropriately and share it with future generations. If the last couple centuries focused on transporting energy and people, then this century is about moving information. NASA currently communicates with over 100 spacecraft, placing increasing demands on legacy systems to keep up with all the generated data. The Space Communications and Navigation Program, known as SCAN, was founded to operate and evolve NASA's networks around the world for future science and exploration needs. Certain missions require maximum connectivity with the Earth, and so they communicate through a series of relay satellites circling the planet, known as the Tracking and Data Relay Satellite System, or TDRS. The largest customer for TDRS is the International Space Station, where it is imperative to remain in constant contact with our astronauts and cosmonauts on board. Interplanetary missions utilize SCAN's Deep Space Network, or DSN. The DSN is a series of terminals featuring the very largest of NASA's antennas to reach far out into the solar system and beyond. The navigational assistance provided by the DSN is so good, we can place multiple spacecraft within proximity of each other, such as with the Mars Science Laboratory entry, descent, and landing. This event was monitored by orbiting spacecraft and transmitted back to the Earth once the rover was safely on the surface. The orbiters continue to monitor the progress of the rover, and together they form a communications network at Mars to work these signals back towards Earth. Now, despite these advances, we are actually leaving up to 95% of our data on board our spacecraft, never to be recovered. Imaging and remote sensing capabilities have far outpaced our ability to transmit their data back towards Earth. The fundamental reason we explore, information, is being limited by the communication technologies we utilize today. Our universe is dynamic, and one has to wonder, what are we giving up? What is in the data between the images? What all are we missing? And how can we do better? Now, here on Earth, fiber optic technologies have enabled significantly faster data rates. And although it's not practical to run an optical fiber all the way back from Mars, space laser communication technologies can enable similar performance in space. The current renaissance of laser communication technologies can offer up to 100 times the data rate at a fraction of the mass of radio frequency-based communication systems. An early proof of this was the Lunar laser communications demonstration, where a spacecraft orbiting the moon acquired a laser beacon from Earth and was able to transmit at a rate 6 times faster at 25% less mass than the RF system. Through this laser link, we were able to communicate video and sent pictures of the Mona Lisa to the moon and return them back to the Earth, all error-free. At these rates, we could communicate 30 channels of high-definition video simultaneously. And the current laser communication systems under development offer an even further increase in performance. The next step is to take laser communication technologies and evolve it into an operational system for missions to utilize. And the Glenn Research Center's Integrated Radio and Optical Communications Project, known as IROC, aims to do exactly that. IROC levies the robustness of the existing radio frequency network and combines that with the emerging high-speed laser communications into a single package to remove the bottleneck in returning the information back to Earth. IROC's combination of operational with emergent technologies is very analogous to the American combined steam and sail ships when boilers were first being introduced in the 1800s. At the front of the IROC system is a combination of an optical telescope and an RF antenna called a telantenna. You are looking at a prototype telantenna for laboratory testing, which aligns the laser beam down the center of the RF pattern. The flight model telantenna is made out of very lightweight materials, including a gold-plated molybdenum mesh for the RF system provided by Northrop Grumman Astro, and lightweight composite mirrors provided by Vanguard Space Technology and GRC for the laser system. The full telantenna spans 3 meters in diameter and attaches to a compact, lightweight vibration isolation platform for stabilization. And this is provided by Applied Technology Associates through a Small Business Innovation Research Contract, or SBIR. Now, as anyone who's given a presentation with the laser pointer can tell you, aiming a beam very accurately can be challenging, and this is especially true for space communications. Over large distances, the beam may expand to about the size of Texas, and this may seem large, but from Mars, this is still essentially trying to place a point onto a point. Precise pointing of our telantenna requires new technology development. So GRC is working with the Optical Physics Corporation through another SBIR to improve the accuracy of small, lightweight star trackers for deep space exploration. The fundamental concept of star tracking goes all the way back to the beginnings of maritime navigation. And here, it is combined with modern optics and electronics for improved fidelity in space. An IROC-equipped craft uses this modern technology to first acquire images of the stars. It takes those images and fuses them together to form patterns. These patterns are then compared with an online starfield database, first to determine exactly where the spacecraft is pointed, and then to determine where to project the communications beam to illuminate the ground terminal back on Earth. Precise actuation of this beam is accomplished through mechanical means in a system being built by Balcones Technology, as well as a series of small, fine-pointing mirrors. The spacecraft data is placed upon the laser beam in a process called modulation, which is performed by IROC's Software-Defined Radio, or SDR. The SDR has heritage in Glenn Research Center's SCAN testbed project, which is currently flying on the International Space Station. The SDR team is developing the optical functionality to support varying mission parameters, to prototype a radio capable of software reconfiguration based on a Harris Corporation platform to evolve during the mission as new technology and requirements are developed. The output of this optical SDR places the spacecraft data onto the laser beam, which transmits this signal across the IROC laboratory using small telescopes to be evaluated for both beam quality and data integrity. IROC is also helping to transition NASA from having a series of individual point-to-point links to realizing a true solar system internet through the advancement of network protocols tolerant to the delay, disruption, and disconnections that are inherent in all space communications. These protocols are prototyped in the laboratory and evaluated to optimize parameters such as efficiency, reliability, security, quality of service, and interoperability with our spacefaring partners. Data traffic is generated by an instrumented robot in the laboratory and sent across the prototype IROC communications link in the laboratory using orbital predicted connections to evaluate the delay-tolerant networking protocol's ability to successfully route this information back to the Earth ground terminals in the most efficient manner. A version of DTN is now used on the ISS and will continue in future missions. Over 93% of Americans witnessed Neil Armstrong place our first steps upon the moon, as downlinked through the Australian tracking station. And then we left.
99, proceeded, 3, 2, 1, ignition. Right away, Houston. Vector good. Ag thought.
Whether you were in the control room back then, pioneering through both tragedy and triumph, or working a console in space operations today, or at home watching the display, waiting for the signal, the experience is the same. Nothing changes. Watching, waiting for the telemetry to arrive, to tell us the system is okay, so we may once more explore the unknown. It is our charge to put into place unbridled communication technologies which will allow all of us to share in the first human presence on Mars. Tune in and join us on our next journey throughout the solar system. We have an opportunity to learn so much more and lay the foundation for the next generation of discoveries. I would like to recognize the NASA communication teams, industrial and academic partners who strive to make all of this possible. And I really want to emphasize that it takes all kinds of people to pull it off, from the scientists and the engineers, technicians, operators, facilities, management, resource analysts, safety, legal, and of course outreach to bring these very messages to you. Thank you all.